Hello, in this video I'm going to look at the translations of the graphs of sine and cosine functions. So basically we know that you have these functions that we can call, for instance, like f of x equals to let's say cosine of x. But let's say that we were to introduce a few translations. So like for example, like if we were to say f of x minus let's say like pi over 2, this is the same thing as cosine of x minus pi over 2. Now the only difference you might wonder is what effect does the pi over 2 have on the equation? Well, to be a bit more specific, basically you're going to have to shift the graph by pi half radians. This is to the right. Now, similarly, if we introduce like constants that will shift the graph of cosine of x, which we can draw that up here just so that we have that as a reference, for example. Like, what does cosine look like? Cosine looks something like this, where you have that it's defined, or its period is from 0 to 2 pi, its minimum is at 1, its maximum is at 1. So basically, like when we're saying like that we're shifting the graph of cosine of x, we mean that we're going to move it over by pi half radians. So for example, I know that that basically that my starting point would be at pi over 2. So essentially I have that that would be pi over 2, and then of course I have that my endpoint would be not 2 pi, but plus pi over 2, which in this case is going to be 5 pi over 2. Now, in any case, one way that you can kind of look at it is that you know that the period of the function is 2 pi, meaning that you know that it moves in phases of 4s, so in that case you have pi over 2 that will increase every single, kind of like important point, or, kind of like the phase shifts. So you know that you have like 3 other points to have to look for, but it's actually a lot easier because you know that it's increments of pi over 2. So in that case, that would be pi. That would be 3 pi over 2. And then this would be, well, this would be 2 pi in actuality. So again, these are just the important points that you have that would represent, the shift change, for example. Now, in this case, like that means that I can actually just draw the graph of cosine. So in this case, I have that I just need to label it respectively. Um, like, okay, so like let's say that that's pi over 2, and then we'll just put that that's 5 pi halves, and then right over here, that's going to be the midpoint, which in this case is 3 pi over 2. And then over here, you have 2 pi. And then over here, you have pi. Now, let's go ahead and say that that's -1, and we'll just say that that's 1. So we have a graph, or we have sets of points right here, right there, and then another one right there. Now, you might wonder, like, how did I know that? Well, again, if you kind of think of it that you're just shifting the x values over by pi over 2, does anything really change about the y values? And the answer is no, it does not. So in this case, like, we'll just go ahead and just connect the dots. So we have that this is going to look something like that. Okay, so it's a bit of a rough sketch, but you get the generic idea that the graph of cosine is actually just being shifted. Now, one thing that you could possibly do, and it's not really always recommended, is that you change your axes. So you know that, for example, that the graph would have been shifted by pi half units. So in that case, that means that basically you're just relabeling this as 1. This is going to be -1. But over here, you have to put that somewhere that this is x equals pi over 2. That way, from here, you just say, well, that's just 5 pi over 2. And this is going to be 3 pi over 2. And this is going to be pi. And then this is going to be 2 pi. So what that means is that basically you have these points at the same, kind of like the same y values. So you have this, and then we just mark right there. Now in this case, all you got to do is more or less the exact same thing. So in this case, you have that the graph will go something like this. Okay, so in this case, the graph looks relatively about the same, but at least like when it comes to these phase shifts, you'll notice that having to change the axes is going to be a lot better than having to imagine that it gets shifted to the right, shifted to the left, stretched, shortened, and then moved up or down in the x and y plane. Um, so usually it's discouraged that you change the set of axes. But it actually does help in some cases to think of it like, okay, well, my graph is going to look kind of messy in this case. Now, if we look at other shift changes, we have to consider, let's write it with this color. Like, what if we multiplied the function by f of x? Then in that case, what we know is that definitely this is a type of vertical stretch. Okay, now we've already kind of looked at the function like this, where we have like if we were to introduce a constant within the equation, and we know that that's basically the horizontal compression or the horizontal stretching. So in this case, like this is our um, horizontal stretch or shrink. But you can also think of it as kind of like a compression. Now the other one that we just kind of mentioned, for example, is like if you have x minus c. Basically, this is the horizontal translations, but it's basically just shifting the equation left or right. Now, the other that I'm going to introduce here is like if I have f of x plus d. Basically, this will shift up or down. These are the vertical translations, and this is the horizontal translations, respectively. So in this case, like, you have to be able to kind of like look at the different graphs and, their translations and whatnot. Of course, like the vertical stretching wouldn't necessarily, or it does account for like if it's negative, like if a is negative, like what does that do? And similarly, like if you have values over here that are negative, like what does that do? Okay, now let's actually look at a graph, and we'll just say that we have y equals 2 sine of x minus pi over 4, and then we'll just have like plus 1. Okay, now in this case, one thing that we have to make note of is that the equation sine of x, we know that if we draw the graph of sine of x, that it looks something like this. And it has a period from 0 to 2 pi. And these points are like -1 and 1 respectively. So the thing to note is, like what's happening. Well, I know that there's a stretch of 2 units, and that's vertically. I also know that there's a shift of pi 4 radians to the right. And then I know that there's going to be a vertical shift by 1 unit. Now, in this case, like what we can do probably is just identify certain things. So first off, I know that the amplitude is um, 2. I know that the phase shift is going to be pi 4 radians to the right. And the vertical translation is 1 unit up. 1 unit up. Okay, now we also need to identify the period. So in this case, the period, it's still actually the same because it's going to be 2 pi divided by 1, which is just 2 pi. So that's still the same. Now, in this case, like what we can do, for example, is that knowing that the period is 2 pi, well, in that case, you know that it moves in waves of 4s, so that's going to be pi over 2. Now, what that does is it basically tells you that your starting point is pi over 4, and then the next point is going to be 3 pi over 4, and so on. So if you want, you can do it like that. For some people, it actually just, kind of like helps them to think, well, if I know that the starting point is now pi over 4, and I know that the end point is 2 pi plus pi over 4, then in this case, why don't I just kind of say that I can just find the midpoints respectively? Because in this case, like if you were to like just do it that way, then potentially, you could do it that way also instead of doing the plus pi over half, plus pi over half, and so on. So like for example, if you do that, then the midpoint over here is going to be 5 pi over 4 because you just add the two endpoints and divide by 2. If you think of it kind of like an average, it's the same thing. Yeah. So then from there, you kind of just do it the same exact way, like where you just say that that's going to be 3 pi over 4. And you can kind of see that there's a pattern, 1, 3, 5, and then of course that's going to be 7, so 7 pi over 4. But how did you get that? You just added 9 plus 5, which is 14, divided by 2 is 7, so 7 pi over 4. Okay, now in that case, that just tells you the important points. So if you go back over here, does anything really change? Not really. The only thing that changes is that you have that there's a vertical stretch of 2 units. Okay, now that means that we can go ahead and just draw our graph of our equation. So let's go ahead and say that, for example, that we go ahead and we mark pi over 4, and then we have 3 pi over 4, and then we have 5 pi over 4, and then we have 7 pi over 4, and let's go ahead and just extend this just a little. And then we have 9 pi over 4. Okay, now in this case, like I have to note that this is going to be 2 and that this is going to be -2. Now the graph actually still maintains the same shape, so you have that important point would be at 0 and then at 1 and then at 0, and then not 1 but 2, and then at -2, and then at 0. Now you can go ahead and try to, say for example, make a table where you plug in pi over 4. Like if you have you have the x and then you have the pi over 4. But then in that case, you would have to also do x minus pi over 4, um, which is actually just 0 when you plug in. I don't like when it does that. So like you know that it would be 0. So in that case, like if you were doing sine of x minus pi over 4, then in that case you're doing sine of 0, which in that case is just 0. So multiply that by 2 though, and uh, you get that that's going to be 0 also. Um, you know what? Actually, you know what? We didn't account for the translation of 1 unit up, so let's actually go ahead and utilize this idea of changing the axes. I know that we're not supposed to do that, but unfortunately I didn't realize that um, my scale was not accounting for that. So that would be -1, and somewhere we'll just indicate that this is y equals 1, and then that means that I need to change this also. Okay, so yeah, normally we would probably just draw like a dash line. That way it looks okay. And you can still say that the amplitude is 2 because 2 plus 1 is 3, and then 1 minus 2 is -1. Okay, so in this case, we'll just go ahead and connect the dots. So we have that this graph is going to look something like that. And then we'll just go ahead and kind of bring this up and then over. So this is my graph of sine, 2 sine. So like y equals 2 sine of x minus pi over 4. And then that's +1. Now, make no mistake that in this case, the domain is still the same. So like, for example, you have that the domain is still -infinity to infinity. However, the range is now different. It's from -1 to 3. And then that's it. Now check this out how again how I needed to account for that 1 unit that shifted up. So like if I was to, let's say for example, go to our graph of sine, so we can see that this is the basic sine function, like 0. Actually I think that, let me see. Oh, there we go. Yeah, so this is the basic sine function where it has like one period of 2 pi. Now, in this case, what this graph does is it accounts for all of the changes that would have to be made. So for example, a was equal to 2, and then b was equal to 1. Now c, unfortunately, c was the value pi divided by 4. So, and yeah, go back over here. That's going to be minus pi over 4. Now the d was actually equal to 1. Okay, so, and we see that the original graph is right here, and that the new graph is right there. So see like how we have 3 pi over 4, we have, let me see, 3 pi over 4, oh wait. Yeah, let me just introduce the vertical translation of y equals 1 because that gets a little confusing with how it passes through this point. So in our graph, we have the horizontal axes, y equals 1. So pi 4, 1, that's correct. 3 pi over 4, 3, that's correct. 5 pi over 4, 1, that's correct. And then it closes over here at 9 pi over 4, that's correct. But see like how these x-intercepts, it gets a little weird in terms of like, what are these x-intercepts? So yeah, just try not to get confused in terms of like if it's passing through y equals 1, how come down over here it says 7 pi over 12? That's because we didn't this graph doesn't necessarily account for that horizontal translation, but you can kind of see that it really does though, because you see like how it's shifted up 1 unit. Um, Let me see. Okay, so yeah, so we see that this graph definitely does give us exactly what we wanted. Now, another case, I have that um, I can probably just show you on how exactly, let's see, what effect would each of these have on the equation. So, actually, let me just go ahead and just reload the graph. Mm, yeah, let's just reopen the graph. That way, we can just look at it from here. So let's look at the function sine. So like A, we see that it's a vertical stretch. B, we see that it's a horizontal compression or stretching. Okay, let's go ahead and just reset these to 1, and let's go back to 1. Now with C, we see that it's shifting the graph to the right. Now you can see that in some cases it actually does tend to overlap. Uh, that's because of the fact that it's periodic and it's moving in waves of 2 pi. So in that case, like this is just moving it to the left and to the right. Um, Now if we look at D, see at D, it's just moving it up and down. Okay, so it's just moving it up and down. Now that would be the same thing as it relates to the cosine function. How, if we just go ahead and play with this, it's just stretching it vertically. And here you can see the kind of like the table of like what's happening with the points. And then like with B, so like I could do this too, and it gets like all crazy, where it's just gonna do all kinds of things. But it's a lot better to just kind of do it like one step at a time. Like if you do like -2, and then if you do maybe like 4, or let's just do 3, and then like over here, what if you just do like -3, and then let's just okay, so like for this one, maybe we could just move it up by like 2 units. Or just have like 1.5. Why don't we do that? Okay, so in this case, like notice that the graph looks completely different from the original, from cosine. First off, we have that the period is actually shorter. Second of all, we have that it's stretched, and then we have that it's moved up, and all kinds of things. So we see like, how these values, they change a whole lot in this case. Like there's a lot that, did change, especially like with the the amplitude. So in this case, the amplitude is like way different on top of that. So these are kinds of changes that we do have to account for. And it's very it's a little more complex than the original translations that you learned. But in either case, like if you kind of like just go one at a time as it relates to the A, the B, the C, and the D. Now in algebra, most likely you use like A, H, and K, for example, which is more or less the exact same thing. So you could kind of like just learn or memorize what each of these constants will do to the original graphs of sine and cosine. Now, for example, we can look at another graph, for example, um, like if we were to have y equals, so like if we have that we want to graph, let's say that we have the graph of negative cosine of 3x um, yeah 3x minus pi, and then we'll just do like plus 1. Now this graph is a little more complex in the sense that we do have to do a lot of things to it in terms of like, okay, we need to figure out what is the period, what is the phase shift, and all those sorts of things. So we can say, first off, we know that there's a reflection over the x-axis. We also know that mm, there's a horizontal stretch of the 3 units. And then we do have that there's a vertical translation of 1 unit. Okay, now there's actually one more. Okay, and that one more is determined by how we rewrite the equation. So negative cosine of 3 times x minus pi over 3. Okay, so I had to rewrite it so that way I can figure out like what is the phase shift. So we have that there's a shift of pi 3 units to the right. Okay, now we could probably do this in a way that either changes the set of axes, or we can probably just account for the shift changes and all that kind of stuff. So first off, I know that the amplitude is 1, so the amplitude is just 1. Now the period, okay, this is where it gets a little interesting. The period is going to be 2 pi divided by 3. Now, in this case, okay, so that's the period. But note that you're moving over by pi 3 units. So in that case, that tells you what your new starting point is and what your new end point is. Now, remember that you always take the period and you divide by 4. Well, if you do that, that basically gives you a shift of pi 6 units for every single important point, if that makes sense. So we know that it's going to start at pi over 3, but that it's going to end at 2 pi plus pi over 3, which in this case is 7 pi thirds. Now, in this case, it's up to you, like, on terms of, like, do you prefer to, like, do you prefer that you're doing the shift changes from pi over 3 to pi 6 and so on, or do you rather just find the midpoints and then just go from there? It's really just preference. Um, but if we kind of think about it, um, we know that, okay, so pi 3 plus pi over 6, that's going to be pi over 2. Okay, so we know that it's going to go from pi over 3 to pi over 2. Then from there, it's going to go to pi over 2 to, let's see, pi 6, 2 pi over 3, yeah. And then from here, it's going to go from 2 pi over 3. Okay, so 2 pi over 3 is, well, it's technically 4 pi over 6. Okay, so this next one is going to be 5 pi over 6. Okay, now I'm running out of room, so let's go ahead and say that that's next one, it's going to be pi over 6. So that's going to be pi. And finally, the last one, um, let me see. I might have gotten, hang on. Yeah, so uh, this right here, let's not clear that, but this right here should be pi. Yeah, I just noticed that just now, because we have that the endpoint would have been 2 pi over 3, but if we have a phase shift of pi over 3, that's going to be just pi. Okay. Yeah, because I'm like, wait, we're going to have more points than needed. Okay, so these are the correct phase shifts in this case. So it's good that I uh, used pi 6 instead of doing the method of midpoints from the, like, yeah, that was a bad error. But it's good to always catch those. Okay, so now remember that for each of these, those have those important points. Now, you could probably make the graph if you want, like the table, if you want to do it like that. But you really don't have to technically, as long as you kind of know like which one is which. So, okay, so let's go ahead and just draw our x-axes. Okay, so we'll say that, for example, that this is pi over 3, and we'll say that this is going to be pi. Okay, so this is going to be relatively the midpoint, and then this is going to be another midpoint. That's another midpoint. So this will be 5 pi over 6. This will be 2 pi over 3. And then this will be, yeah, okay, so, 4, okay, so then this will be pi over 2. Okay, now we just have to check in terms of like, is there any vertical translations? There is. So there's one at 1. Okay, so in this case we have that there's a vertical translation of 1 unit. So we have 1. Now it's good to go ahead and just use like another color so that we can indicate that this is sort of like a translated y x-axis. So it's yeah, we have the translated axes, and then it's 1 unit. So it's 1 unit up and 1 unit down because of the amplitude is 1. So okay, so this is kind of weird. Um, okay, so the starting point would be pi over 3 and at 1, but it's reflected. So it's reflected, and it would be -1, but since it's translated by 1 unit, it's actually going to push it up to 0. Um, we can actually verify this, by the way. Like if you plug it into the equation, you get cosine of pi minus pi is 0, which is 1, but it's -1 plus 1, it's 0. Okay, so we're already off to an interesting start, that you have that it's going to go through here at 0. Then over here, this is where you have pi over 2. So pi over 2 would be 0, but it's actually going to be 1. And again, you can kind of just plug those into the equation if you wanted to. It's not really that difficult because you have 3 pi over 2 minus pi. So that'll be pi over 2, which is 0, so it's just 1. And then you repeat that process relatively the same. So like for example, when you plug in 2 pi over 3, you're going to get 2. So in that case, you have 2 units. And then you have that, it's just reflected. So in that case, you have that it's going to go through here. And then it's going to go through, oh, wait, not that one. Yeah, it's going to go through here. And then it's going to go through here. So all that we need to do essentially is to just make the graph look as close as possible to the sketch. Okay, so this is kind of like a rough sketch of the graph. So we have that this is the equation of y equals negative cosine of 3x minus pi, and that's plus 1. So we have our graph of our equation, and note that the domain is still the same. It's still minus infinity to infinity, but that the range is now from 0 to 2. Okay, because like over here, you have that peak point is 2, and then the low point is 0. So like for example, if we were to go to our Desmos graph, and let's say that we were to change that to -1. So the -1, we know that it just reflects it, so -1. The B was 3. Now the D was equal to 1, so we have that. But then this was going to be, uh, let's see, it's pi, isn't it? Yeah. Okay. So let's focus on the section that we had. So pi over 3, 0, 2 pi over 3, 2, and then we had that the endpoint was at pi 0. Now, of course, like, you know, if you want to know, like, where does it cross where does it cross over here? Well, it crosses, let's see if we can get it. Let's go ahead and plug in another equation, like y equals to 1. That way you can kind of see, okay, pi over 2 and 5 pi over 6, which is the same thing, essentially. Of course, this looks much nicer on this graph, but yeah. Now, of course, you could have probably, let's say, for example, graphed that equation by changing your set of axes, where you would have said, you know, okay, I know that this is pi over 3, and then you just graph this right here, and you're just like, okay, well, I know that that's y equals to 1, so this is x equals to 3. So we know that in this case, you would have to relabel this as that's going to be 2. That's 1. So in this case, you would probably just need to notate 0 down over here. That way you can say, okay, well, the graph of that would look like this, and it probably would be better to just do pi. and then 2 pi over 3, and then pi over 2, and then 5 pi over 6. And I don't know why I drew it small, but yeah, it's okay. So then we have that there would be a point right there. I accidentally switched colors. And then we have a point right there. And then we have a point right there. All that you need to do from here is just connect it. And then that's it. So this section represents the period from pi over 3 to pi. Whereas like if you go back over here, you can see that that's exactly, what I just drew, but just changing the axes. Which is an okay idea, but usually it's actually discouraged to not do that. Mostly because they want you to be able to know, like how did you get these graphs essentially? Okay. Now I would recommend going back to the very beginning of just looking at translations and then just seeing like what do they do in terms of like that should actually just include a shrink also, right? Because yeah, you can actually have that you shrink something vertically in either case, because you probably would be asked, for example, like how to graph certain equations given uh, all the respective shift changes.